Now we're going to look at the application of these techniques to solve some more difficult problems. So, for example, we talked about compositions, which are a number of ways to write an integer as a sum of smaller integers. A natural question is, how many compositions of n have k parts? So for 2, it's either 1 plus 1 or 2, so there's one that has one part, and there's one that has two parts. For 3, there's 1 plus 1 plus 1. That's one composition with 3 parts. There's 1 plus 2 and 2 plus 1. That's 2 compositions with 2 parts. And there's 3, that's one composition with 1 part. There's always going to be one with one part and one with n parts. And again, now the binomial coefficients are starting to show up again. And in fact, the number of compositions with k parts is n minus 1, choose k minus 1. We can hypothesize that from this table. And I'll also start including in these tables the accumulated cost and the average, which are easily computed from these numbers. So, for example, for n equals 4, where the number of compositions with k parts for k equals 1, 2, 3, 4 is 1, 3, 3, 1, the total number of compositions is 8. The cumulated cost is 20. That's 1 times C41 plus 2 times C42 plus 3 times C43 plus 4 times C44. So that's 1 plus 2 times 3 is 7, plus 3 times 3 is 9, plus 7 is 16, plus 1 times 4 is 20. And divide the 20 by the 8, you get 2.5. And do that same calculation for n equals 5, you get an average cost of 3. So the average goes 1.52, 2.53. You can probably see a pattern there as well. But what we'll do is use the symbolic method to compute this average. Okay, so here's the definitions. We're interested in the class of all compositions. Recall that we can write compositions as the number in unary and just put a bar to indicate the division into a sum. So 12 could be 1 plus 3 plus 1 plus 5 plus 2, and that's an example. But now our parameter is the number of parts. So we have an ordinary bivariate generating function, z to the c times u to the number of parts in c. So what does the construction look like? We want u to mark the number of parts. We're going to use our same construction that we used before. A composition is a sequence of integers. An integer is a sequence of objects, but not including the empty one. So for every integer, we just want to mark that with u. So that's the construction. Just add the u to the inner sequence. That immediately translates to the ordinary bivariate generating function. U sequence greater than 0z is u times z over 1 minus z. Sequence of that is 1 over 1 minus that. Simplify by multiplying by 1 minus z, and we get the expression 1 minus z over 1 minus z u plus 1. To compute the horizontal ordinary generating function, we take the coefficient of z to the n in that, and that's very similar to our calculation for binomial coefficients. It's just u plus 1 to the n minus u plus 1 to the n minus 1. So the number of compositions of n is just evaluate that at 1, which is 2 to the n minus 1. The accumulated cost is going to be differentiate and then evaluate at 1, and that's n times 2 to the n minus 1 minus n minus 1 times 2 to the n minus 2, which simplifies to n plus 1 times 2 to the n minus 2. Very simple calculation, and then divide those two, and we get the average number of parts in a random composition of n is n plus 1 over 2. And that's what we observed in the table on the previous slide. Okay, let's look at parameters on trees. Again, these are questions that maybe might be a little more difficult to analyze, but they're straightforward using this method. So what's the expected root degree of a random tree with n nodes? So this one has root degree 4. The root's got 4 children. Or how many leaves are there in a random tree with n nodes? This one's got 14 leaves. Parameters like this, again, we can analyze by developing a generating function equation for the ordinary bivariate generating function using the symbolic method, then extracting coefficients to get the horizontal generating function, and then evaluating at 1 to get the answer. And this is a practical question in plenty of applications. This is a big random tree. How many of the nodes are leaves? So this is all random trees. These are ordered, rooted trees. And so again, we're asking how many trees are there that have n nodes and k leaves? So there's 1 for 0 and 1. For 1 and 2. For 3, there's 1 tree that has 1 leaf, and there's 1 tree that has 2 leaves. For 4, there's 1 that has 1 leaf. There's 3 that have 2 leaves, the ones in the middle, and there's 1 that has 3 leaves, the one at the top. And for 4, now these are not binomial coefficients. So this is the distribution, and we can go ahead and compute the accumulated costs as before. So for 4, the accumulated cost is 1 times 4(1), 2 times 4(2), plus 3 times 4(3), so that's 1 times 6 times, plus 6 plus 3, that's 10. And there's 5 of them, so the average is 2. And the next one is 35, the average is 2.5. And again, you might have a hypothesis for the number of leaves just from this table, but the question is to prove it, which is straightforward. It turns out to be n over 2, and we'll prove it on the next slide. So we're going to use the same construction that we used before for trees, but we're going to carry through the transfer for ordinary bivariate generating functions, not just single bivariate generating functions. So our parameter is the number of leaves in the tree. What's a tree? A tree is either a root, or it's a root with a sequence, a non-empty sequence of trees. So that root is a leaf. That one's got no trees below it, so that's what we mark. So that construction immediately translates to generating function equation, just using the symbolic method. And it's very similar to the one that we saw when we generated trees. In fact, if you evaluate at u equals 1, you get exactly the same equation that we had for trees, which is the coefficients of the Catalan numbers. So that's the number of trees. And cumulated cost, differentiate with respect to u and evaluate at 1. And there's some calculation omitted here. And so that's the result that we get. And coefficient of z to the n and 1 over 1 minus 4z is 2n choose n. So now divide those two and you get n over 2. That's the average number of leaves in a random tree. And I admit I omitted a little bit of calculation here. You might want to check that. You can see some wondrous properties of square root of 1 over 1 minus 4z. So that's leaves in random trees. And again, that's what we observed, and you can also go ahead and compute the standard deviation, and it's concentrated. So a big tree, half of them are leaves. What about root degree? What's how many trees are there with n nodes and root degree k? Again, these are the counts. So for 4, there's 2 of them with root degree 1, the bottom 2. two of them with root degree 2, the middle two, and one with root degree 3. And for 5 nodes, that's the distribution. And again, we can go through and compute the cumulated costs, and it goes 1.5, 1.82, not so clear what the result is going to be in this case, but we'll use the same method to go ahead and compute the average root degree. So it's the same class, it's the same construction, we're just going to mark the trees in a different way. This time, what we're going to do is a random tree is a root and then a sequence of random trees, but we're going to mark that first sequence with our variable u. So coefficient of u to the n, so that the coefficient of z to the n u to the k, and that is the number of trees with n nodes and root degree k. So that immediately gives, again, the ordinary bivariate generating function equation, and evaluated z of 1, again we get the what we got for regular Catalan. If we differentiate with respect to u and evaluate with 1, we get a 1 over 1 minus g squared term, and there's a little magic calculation here as well, having to do with the fact that g of z has this special generating function 1 minus square root of 1 minus 4z over 2, and extracting coefficients gives the result that the average number of leaves is gn plus 1 over gn minus 1, which the ratio of the Catalans, there's a little bit of calculation. It's 4 minus 6 over n plus 1. Minus 1 is 3 minus 6 over n plus 1. And that's what we observed on the previous slide, 1, 1.5, 1.8, and 2. The average number of leaves in a random tree with n nodes is about 3. It converges to 3. And again, that's an interesting fact to know for certain practical applications. And it's available with some calculation directly via the symbolic method. Here's another famous application. This is about rhyming schemes for poems. So this is a limerick. There was a small boy of Quebec who was buried in snow to his neck. When they said, "Are you frizz?" he replied, "Yes, I is, but we don't call this cold in Quebec." So that's got the rhyming scheme, as do all limericks, A, B, B, A. Or if you want Robert Frost, 2 roads diverged in a yellow wood, and sir, I could not travel both. And be one traveler long I stood, and looked down one as far as I could, to where it bent in the undergrowth. That one's got the rhyming scheme A, B, A, B. So a natural question, which actually lots of people have studied from musicians to poets, is how many different ways are there to rhyme a poem? So that's a parameter, and so we're going to ask the question, if I have an n-line poem, how many ways are there to rhyme it with k rhymes? So it's a 2-line poem, there's only 2 possibilities. Either the 2 lines don't rhyme or they do. That's A, B, and AA. If it's 3 lines, well, you could have ABC, nothing rhymes, or you could have ABB, the second 2 rhyme, or you could have AB and then A, or you could have AA and then B, or you could have AAA. But there's lots of strings of 3 letters that aren't here. Well, the first one's always got to be A. The second one's got to be either A or B. And then the third one can only be C if the first 2 are A and B, and so forth. So you can think a little bit about what the constraint is here. Anyway, here are the numbers. So for a 3-line poem, there's one of them has just 1 rhyme, that's AAA. One of them's got 3 rhymes, that's ABC, and the rest of them have 2 rhymes, ABB, ABA, or AAB. And then that's the answer for 4. So that's the distributions, and we can also do the cumulative costs as well, but let's look at the generating function. So the class of all rhyming patterns, and our size is the number of lines. Our parameter is the number of rhymes with k lines. We use our ordinary bivariate generating function as before, and now the key is what's the combinatorial construction look like. And this one actually is a vertical construction. What it says is that you're going to have your first thing, your first object is going to be rhyming scheme A, and you can have a sequence of any number of those. And then after that, you're going to have a B, and you can have a sequence of any numbers of A's and B's after that. And then you can have a C and a sequence of any numbers of A's, B's, and C's after that. That's the construction for the class of all rhyming patterns. And that immediately gives the vertical OGF for if we fix the number of rhymes to be k, this is the generating function for the number of poems of size n that have k rhymes. That's the vertical OGF. And actually this turns out to be numbers that are well known in combinatorics and appear in many, many other applications that we're not going to have time really to talk much about, although we'll see them again, and you can certainly read about them in the book. These are called the Stirling numbers of the second kind, and we'll see them again in another application in this lecture. Turns out about k to the n over k factorial n-line poems have k rhymes. And just the Stirling numbers of the second time, these are the frequencies that we observed. And again, they're very well studied. The horizontal OGF is known as the Bell polynomials. The vertical OGF is the one that we just determined. Okay, these are the Stirling numbers of the second kind, and we don't have explicit expressions for them, but we'll see them again. So that's several examples of ordinary bivariate generating functions studied with the symbolic method.